Greater London covers an area of 1,580 square kilometres or 610 square miles in old money. Not only does it cover a significant geographical area, but it also has a large geological spread. From clay soils in the northwest to chalky soils in the south, architects, engineers and contractors need to be aware of the ground beneath their feet, as conditions can vary quite widely over distances of a few metres or yards. This programme will explore various soil types and build-ups. We've chosen to focus on the conditions prevalent in the London area, but the issues will have a general applicability across the country and more widely. With us to sift through the information, we are delighted to have John Burland, Professor Emeritus at Imperial College London, who specialises in problems relating to the interaction between the ground and masonry buildings. He's advised on the stability of the Big Ben clock tower as expert witness for the Jubilee Line extension, and he was a member of the Italian Prime Minister's Commission for stabilising the Leaning Tower of Pisa. So, John, welcome.
Hello.
Thank you very much indeed for coming in. This may be a more anodyne conversation than you may be used to in your jet-set lifestyle, so let's start with a few basics. There's all talk in these circles of soil maps. What's the sort of generic things that we're looking at in soil maps? What are they?
A soil map would place on a map different types of soil as they are near or at the surface. So it would be a representation of what you might see if you were fairly expert or if you dug holes across the landscape. It would tell you what is there
And
near the surface.
Near the surface means what?
Within a few metres.
Okay, fine.
1
And then
or 2
there's
metres.
so those are reasonably detailed soil maps, or you can have detailed soil maps. But then there's this thing called inferred soil
Yes.
attributes. What can we infer from a soil map?
We have to infer a lot. A soil map will tell you a lot, and it'll tell you very little. A lot, it would tell you the geological origin of the soil. It would give it a name, and experience has been built up over the years as to how certain types of soil which have been named, like London clay, how they behave. But it won't tell you about the water conditions. It won't tell you about how strong the soil is. There's a lot of detail which you would then have to work out by direct observation or by experience in a given locality.
Okay, good. Well, on screen now we've got a soil map of London,
Yes.
which points out the different types of soils that we can find in the general Greater London area. But can you explain, first of all, why these soils are where they are?
Yes, it goes back to fairly lengthy geology time. And if we start at the bottom first, the chalk was laid down in what is called the Cretaceous period. So a considerable thickness of chalk was deposited. And then above the chalk, sands were laid down. They're called the Thanet sands. And then we get a stratum known as the Lambeth group. And overlying that broadly, we have the London clay. So they're in a series of successions of layers. And then the important thing is that with time, they get warped, so that under London there's a dish. The chalk is in the form of a dish, with the London clay sitting in the dish. So as you go across from north to south, the chalk is at the surface, and then it gets deeper and deeper and deeper till you get to the bottom of the dish. And then when you come out at the south, you're at the North Downs, where it emerges again.
Right, and the Lambeth group is a mixture of...
It's a very
various
variable
types.
deposit with limestone bands, clay bands, sand layers. It's a rather treacherous, or in the past is believed to be, a rather treacherous stratum.
And treacherous in as much as you were saying earlier that maybe the tunnels are few and far between in that area precisely because
Yes,
of...
down to the southeast of London. If you look at a London Underground map, until the Jubilee Line extension was built, there are almost no tunnels, because tunnelling conditions in the Lambeth group using traditional methods were just too difficult. You could get water gushing in unexpectedly and drowning the tunnel and causing terrible problems.
Okay, well that's a good starting point for the types of soil. We've got again this drawing of the soil map of Greater London with a key at the bottom right-hand corner. Let's go through a few of them, if you would, in terms of wet soils. But what's the benefits and problems of wet soils?
Well, wet soils is rather an agricultural term, actually. It means there's a lot of water in them, and if it's soft as well, it's boggy, and that's not good for building things on or for taking a bulldozer across. So it creates construction problems for the engineer. But the other thing we mustn't get confused about is not only do you have the problem of wet soils, but you can get quite firm soils with water in them. And what is really important there is what is the pressure of the water and how easily does it flow through the soil. Those are the two really important things, and you don't get those from a map.
Right, good. Well, just on actual water, soil moisture deficit, one of these confusing terms, well, it confuses me anyway, which is the amount of rain needed to bring soil moisture content to full capacity. But I read, just so you can explain this to me, saturation occurs when the soil moisture deficit equals minus 10 millimetres. That is when there's a water surplus.
There's an excess of 10 millimetres rainfall. And the reason for that is empirically they have found that you need a little bit more rainfall than the soil can actually absorb as it's wetting up. And of course the difference is the runoff.
Right.
The water disappears.
So it's just a contingency number.
It's an empirical number that has been derived by experience.
Okay. Let's just talk about wet soils finally in terms of improving the drainage of wet soils. And like you say, this has implications for agriculture, but also in terms of stability and bearing capacity of buildings. What can be done really to dry out, for a better phrase, wet soils?
I mean, from an engineering point of view, the most important thing you can do is to drain it. Arrange in some way, either by pumping or by gravity, for the water to drain out. Or you cut it off, you stop it flowing in. For example, under the car park at the Houses of Parliament, which I was involved in, the deep underground car park there, when the site investigation was done, they found very thin sand layers under where the car park was going to be. And the problem was that if water flowed in, it would blow the bottom out of the car park. And I would have succeeded where Guy Fawkes failed. And the way we dealt with that was to put concrete walls down and cut the water off. So if you can cut it off or if you can drain it, that really is the most important thing to do.
Okay, right. Acid and alkali soils. Again, I know a lot of these are kind of surface agricultural terms that landscape architects might be more concerned about than maybe structural engineers. But again, where might we find these soils and what should building designers be mindful of?
Well, I think that the most important issue is whether you've got acid conditions. You don't encounter them very often, but there are certain conditions where the acid will attack a concrete pile or a concrete foundation. It's not a great problem. Where it is a problem, actually, is when you're dealing with what is called brownfield sites, where you might have had a gas tank or a chemical plant or something of that sort that's left some nasties in the ground. This is where it is very important to know whether you've got alkali or acid conditions.
And that's really from soil testing rather than any soil map of...
That would be from soil testing, yes.
Right. Clay soils. We've got on screen now the British Soil Classification System triangle. They come in various shapes and sizes, these graphs. But can you just talk us through maybe the differences in terms of clay and silt and how you'd find out which is which?
Yes. Okay, well, let's start with boulders, because everybody can see a boulder. That's more than 2 or 3 centimetres in diameter. You can see it, you can handle it.
Sorry, a boulder is more than 2 or 3 centimetres?
Yes, it would be this kind of size. And they can be quite treacherous if you're banging a pile into the ground, if you've got a tunnel machine going through or you're excavating. Below that you'd get gravels, which are rather smaller than that, down to perhaps 0.5 centimetre in diameter, perhaps a bit less than that. Again, we all know what a gravel is. You can see it, you can handle it. You see it going into concrete. Below that you have sands. Now they're still visible to the naked eye. even a fine sand, you can just see the grains. So you go from sands, and then you go into silts. Now silts are still granular, but you can't see the individual grains. It's very important to be able to distinguish between a silt and a clay. And my experience is you can tell very quickly if you take a small sample of the soil, rub it against your tooth, and you can tell straight away by its grittiness whether it's silt or whether it's clay. But you have to be a bit careful when you do that. It mustn't be polluted. There are other ways, but silt is really a very, very fine granular material. And then we move into the clays, and they are flaky. They are made up of tiny little plates of clay particles. They're very greasy to feel, very almost like chocolate. It doesn't taste like chocolate, but it has that feel about it. And it's all on the grain size. We go from the boulders right down through the sands, the silts, and then we're into the clays.
Okay. Just as a disclaimer, we don't actually recommend that people do eat soil.
We don't eat soil.
In terms of London clay, then, what is that? Is it just prone to be found in London area, or is it more wide than
It's
that?
a fairly widespread deposit, actually. It goes across, you find it actually in Paris as well. But it's called the London clay because it outcrops in the London area, and we've given it that name.
And does it have any particular qualities?
It's a very stiff material if you get hold of it in its unweathered state from quite a depth, from a few metres depth. It'll be quite stiff. You'll have difficulty in pushing your finger into it. But it's got lots of fissures in it. If you break it, you'll find lots of shiny surfaces in it. It's actually very good material for tunnelling. That's why we get a lot of tunnels in the London clay. And up to a certain height, you can build on it as well.
Is it got like a bluey tint to it?
The unweathered state at some depth is often called the blue London clay. If you go down a hole in the ground and look at it, it almost has a blue look about it.
Okay, very interesting. Then in chalky soils. Again,
Yes.
just talk us through the benefits and hazards, I suppose, of chalk.
Yes. Well, now chalk was laid down in the Cretaceous period, and it was made up of the skeletons of lots of little beasties, lots of little beasties. And we have a picture here. There's an electron micrograph of chalk, and you can see that it's a very open structure, and here are all the little skeletons of the beasts that lived in that. And it's a very interesting material because it's got quite an open structure. You can see a lot of space in there. We call them voids. But the skeletons are cemented together. So it's quite strong. So that's good. It's not very compressible. So it's in its undisturbed state. It's quite strong. It's not compressible, and you can dig it very easily. But the treacherous part is if you disturb that structure, it can turn into a paste very quickly, which is very treacherous because it reduces in volume, releases water, and it turns into sort of toothpaste material.
Right.
And that can be very treacherous.
And that's done through what, vibration and
It's
addition
done
of
through
water?
mechanical disturbance.
Right.
The other thing about chalk is that if you have it exposed to the atmosphere, because of its structure, when water gets drawn into it, the freezing point depresses. It can draw water in, but once it freezes, it destroys this structure, this delicate structure of the chalk. So chalk can be destroyed by frost action, and it heaves and causes all sorts of problems. You don't want chalk immediately beneath a road surface because the frost can get at it and cause a huge amount of damage.
Because in terms of heave, we automatically assume that we're talking about clay as being the biggest problem, but chalk
Well, with
equally-
chalk, if you get water into it and it freezes, it actually breaks apart. You get some increase in volume due to freezing, and it destroys the chalk structure. It becomes this soft, horrible, pasty material when it thaws.
Right. Well, speaking of chalk then, the deeper geology of the London Basin, we've got a diagram here,
Yes.
which is taking a look of the
Yes.
London Basin area.
Well, I think when you're looking at a soil map, it's very important to try and understand not just the surface, but what is beneath it. And as I mentioned just now, you have the London Clay Basin. And at the bottom of the basin you have the chalk. So if we look here, we have the chalk, and that emerges to the north at the Chilterns, and it emerges to the south at what's called the North Downs, and that's a basin. So the chalk underlies the whole thing, and then overlying the chalk we have the Thanet sands, and you'll find the sands shown here, and then over them we have this Lambeth group which we were talking about, which is very difficult to tunnel, and they emerge here, and then above them we have the London clay, which is over most of North London. That's near the surface. Overlying the London clay you often get gravel, which has been deposited by the River Thames at various stages, and you also get alluvium, which is a mixture of usually of silts and often quite soft clays, recently deposited by river deposits.
And when you say near the surface for the London clay, again, are you talking about
alluvium would normally be very shallow. We're talking 3 or 4 metres. Perhaps.
Right. And the London clay, would
that can be anything up to 30 or 40 metres thick, depending on where you are in London, or even more.
Because of that bowl.
Because of the dish that the basin that we're talking about.
Fine. Right. Okay. All right. Well, look, this is all good stuff. But in terms of practical realities, you've worked on a number of kind of high-profile projects. Yes. So again, we've got another diagram here, cross section through the Jubilee Line extension, yes. Which basically shows the way that the route of the tunnel. Again, can you just explain or tell the story about what you encountered?
Yes. Well, the north part of the tunnel is all in London clay. So it starts at Green Park, and it runs down under St James's Park through to Westminster, and all that is in this beautiful tunnelling material, the London clay, which is traditionally ideal material for tunnelling in. And then we go under the Thames at Westminster, and again we're in London clay until we come down to round about where London Bridge is, because it turns east and runs along the south bank to London Bridge, and then it goes in to the Lambeth group, and this is where they had to bring in special tunnelling machines, because the Lambeth group is this treacherous material with different layers in it. They also drained the Lambeth group because of these high water pressures. They actually drained it temporarily while they were tunnelling through it. So it ran all along the south bank in the Lambeth group, and then it turned north again, back into the London area. So it was particularly that area on the south bank, running along the south, where no tunnels had been driven before, because the ground conditions in the past were too difficult.
All right, well, we can't go. We've done a hasty view of the geology, several million years worth of history in half an hour, but we can't go without you telling us what happened with Pisa. How
Pisa, right.
what you did and what you found and how you solved
Yes.
the problem.
Yes.
And you've got a model to help explain
Yes.
how it worked. Do you want to pull
Yes,
that out?
indeed. The thing about the Pisa Tower is that it is founded on extremely soft material. It's founded on very soft silt, and under the silt is extremely soft clay. And the big question is, why is the Pisa Tower leaning? And everybody believes that it's because it must be rock under one side and soft soil under the other. And that's not the reason why it's leaning at all. The reason becomes obvious when you try and build a tower on very soft material. And here's some foam rubber. So let's build a tower on this soft foam rubber. And here it's going up, and it looks splendid as you go up, and we'll keep it absolutely straight, and we'll keep going. A little bit more. Now it's beginning to get a bit wobbly, but there comes a certain height where it doesn't matter how straight you've made it, it starts to lean, and this is beginning to lean. And it's actually to do with how very soft the material is. It's not to do with its strength. And you can see how it's slowly going over, which is really what the Pisa Tower was doing. And this is perfectly uniform material, but you can still see it's beginning to lean, isn't it? And there it goes.
There you go.
And
history is made.
the Pisa Tower was on the point of doing that because the material was so soft. It's at the critical height at which it just begins to lean.
So it's a critical height we're talking about. So
Yes.
Even if you were to have built that perfectly, I mean, you did that kind of
Yeah.
very quickly,
Yeah.
but if everything was aligned,
Yes.
that still
It
may
would
have
still
helped.
lean. And every child who's tried to build a model brick tower on a soft carpet will know you can spend all afternoon trying to make it straight, but at a critical height it will always start to lean. And it's some very interesting mechanics. It's actually quite, a child can work it out, but it's to do with the softness of the carpet and the weight of the bricks and the diameter of the foundation. And
You say
why-
every child could work it out. Oh, it's a
by
first time I've realised what it
experiment.
was.
By experiment. Every child who's tried to build a tower on a carpet will know that you can only get to a certain
I
height.
just thought it was my shaky hands.
No, no,
so
it's
we've
not.
got a couple of cross sections as well, which we'll show at the moment. But in terms of how you resolved that,
Yes.
again, it's not we're not talking about the bearing strength of the soil
No.
here. We're talking about the sponginess of the soil, if you like.
Yes.
So what was your remedy for it?
The first thing we had to do was temporarily stabilise it to give us time to work out a permanent solution. And the way we did that was to put some lead weights on the high side to stop it falling over. It's like sitting out on the side of a sailing dinghy. And they went on in 1993, and they were very effective in just holding the tower. And then we worked out a permanent solution which involved actually taking a little bit of soil out beneath the high side of the tower and very gently bringing the tower back by a small amount, not enough for anyone to see, but enough to reduce the forces acting on the foundations and on the tower masonry. And we did that. And the other thing we did was we found that each year the water table would go up and down due to very heavy rains in the autumn. And that rising water table always gave the foundation of the tower a little bit of a shove by its buoyancy effect. And we've stabilised the water table, and that effect has now stopped. So it was we reduced the inclination by this very simple way of soil extraction, and we stabilised this very important effect, the water pressures, the water table.
So actually, maybe trying to excavate and underpin it might have been actually hazardous.
It would have been a complete disaster because the tower was on the point of falling over, and any disturbance in this very, very soft ground would have finished it off.
So literally, it was on the verge of falling over.
It was on the verge of falling over.
Fantastic.
Yes.
Well, on that note, ladies and gentlemen, thank you, John, for making it seem like child's play. It's clear that the more you drill down into this subject, if you pardon the pun, the more you discover new layers of complexity. I hope that this programme has been useful to you. Until the next time, from me and Professor John Burland, CBE, Emeritus Professor at the Department of Civil and Environmental Engineering at Imperial College in London, goodbye.